Now let's talk about drift velocity. Drift velocity एग्जाम पॉइंट ऑफ व्यू से भी बहुत इंपॉर्टेंट है और हर एक साल किसी न किसी क्वेश्चन तो इस टॉपिक से रह ही जाता है. सो drift velocity एक्चुअली हमारे पास अगर कोई अनचार्ज कंडक्टर रहेगा तो here it is an uncharged conductor and even if it is not connected to any grid spot, still we find that there are lots of free electrons which keeps moving in all possible directions. And also we know that what is the name of these free electrons? It is electron cloud. So in an uncharged conductor which is not connected to any source, in such type of conductors also we have large number of free electrons, and these free electrons continuously keeps moving in all possible directions. They don't have any particular fixed direction. They continuously moves like this in all possible directions, I passed earlier. And let's denote the velocities like this. For the first relation, for the first electron, we have velocity equals to u1 vector. For the second one, it is u2. For the third one, it is u3, like this. And for nth electron, it is u1. Now, if we find the average velocity through any cross-sectional area, let's consider a cross-sectional area like this. Here, we are interested to find the average velocity, average flow or average velocity of these electrons. Through this particular cross-sectional area, if we are interested to find the average velocity, we can write like this: average velocity, which is equals to u1, u2, u3 plus un divided by un. But since all these velocities are vector quantities, here the vector sum of all these velocities will be equals to 0, because ऐसा तो कुछ इलेक्ट्रॉन इस तरह जा रहा है, कुछ इस तरह भी जा रहा है, कुछ ऊपर कुछ नीचे, अल्टीमेटली सब कुछ बैलेंस हो जाता है, मतलब नेट फ्लो कुछ भी नहीं रहता है. So in that case, this sum of all these velocities, vector sum of all these velocities will be equals to 0. So ultimately we find that the average velocity through this conductor is equals to 0. अगर मान लिया कि इस कंडक्टर के साथ हम लोगों ने कुछ पोटेंशियल डिफरेंस अप्लाई कर दिया, जैसे कि चलिए यहाँ पे एक बैटरी लगा देते हैं, ठीक है. So here the direction of current is from positive terminal to negative terminal. This is positive, this is negative. So the direction of current is clockwise, and the direction of electric field is also along the direction of current. So this is the direction of electric current. The moment you apply this electric field across the two ends of this conductor, the existing electrons, free electrons in this conductor will experience certain amount of force. Actually, the point just now I have said, actually you will be taught in your electrostatics part. Here, there will be an expression like F equals to QE. What this equation signifies? Actually, it signifies that if there is a uniform electric field where a charge Q is placed, then this charge Q will experience certain amount of force. And what will be the magnitude of force? This Q will be equals to this force will be equals to Q into electric field, magnitude of charge into electric field. So similarly, when we apply an electric field E, the electrons in this conductor will also experience the same amount of force. Now what will be the magnitude of force? So we can write force experienced, let it be equation 1. Force experienced by each electron, F equals to QE. Actually it is F equals to QE, but instead of Q, since we are considering single electron, so let's replace Q by E, and here it is capital E, which denotes electric field. Now these F and E both are vector quantities. If you observe at this point, you will see that electric field is acting from left to right. But here is the negative terminal. Negative terminal means it is electron efficient, whereas positive terminal is electron deficient. So the flow of electron will be like this in anti-clockwise direction. So the excess number of electrons will go along this path, and here the existing electrons will be pushed towards the positive terminal. So these free electrons will experience a certain amount of force, and the direction of this force is from right to left. So here these electrons are experiencing a force which is opposite to that of the direction of this electric field applied. That's why F and E are vector quantities, but they are acting in opposite directions. That's why let's put a negative sign here. Now we also know that F equals to ma. For a single electron here, the force, magnitude of force can also be expressed as F equals to ma, where what is m? This is mass of electron, and this is acceleration of electron. Okay. So if we put this equation in the above equation, instead of F we will write m a vector, which is equals to minus E capital E by m. These are vector quantities. So this. So vector a vector equals to minus E capital E vector by m. This is the expression for acceleration with which these electrons are pushed towards positive terminals. Already these electrons are having velocities u1, u2, u3, etc. Now after adding electric field, we are getting another component, another acceleration, which actually accelerates the electrons towards positive. Already all these electrons are having certain velocities. Again, due to this electric field, we have some other acceleration component. So from acceleration, easily we can find velocity. Let's consider from equation of motion. We see acceleration equals to velocity by time. So simply we can say that let's find the expression for velocity. Velocity equals to at. But here in this case, instead of t, we will be using another term, that is tau, which is called as relaxation time. Relaxation time. So now the new velocities, instead of u1 for the first electron, u1, we can write u1 plus a, that is acceleration into tau. Let me explain what is tau later. So this is tau 1. For the second electron, already before connecting electric field, it had a velocity u2, and after the electric field is applied, its velocity gets increased by a quantity a vector tau. Then for electron 3, this is u3 plus a vector tau 3. For nth, it is u1 plus a vector tau. Now what is all these tau 1, tau 2, tau 3, etc.? What all these quantities represent? Actually, these are relaxation times. Relaxation times. That means time interval between two successive collisions. Where we are considering this relaxation time? Actually, in between two collisions, one particular electron moves along a straight line, and just after colliding with another second electron, the direction and velocity gets changed. That's why we are considering these time components as tau 1, tau 2, tau 3, and the average of all these relaxation components like tau 1, tau 2, tau 3, plus dot dot tau n divided by n is equals to tau. So now we'll add all these quantities. Now adding all these quantities, we will have average velocity v, which is denoted by vd. Vd equals to u1 plus a tau 1 plus u2 plus a tau 2 plus un plus a tau n divided by n. Now अभी अलजेब्रा करते हैं, सभी u को अलग कर दिया, divided by n plus a tau 1 tau 2 tau n divided by n. And already we have written here that it is equals to n. Now in equation earlier in equation 1 we derived an expression like u1 plus u2, the average of initial velocity is equals to 0 in equation 1 earlier we have written. And here it is acceleration, then this is tau from here, this is tau. So we have the expression for drift velocity as. Now let's replace the value of a. Earlier we direct the value of a here like this. So ultimately we get the expression for this equation equals to E capital E vector by m into tau. So this is the ultimate expression for drift velocity. So what is drift velocity actually? It is the average velocity. यहाँ पे जो भी हम लोगों ने किया एक्चुअली क्या किया, हम लोगों ने इसका एवरेज वेलोसिटी निकाला, और एवरेज वेलोसिटी इन केस ऑफ ए कंडक्टर इट इज सेड एज it is known as drift velocity. So what is the definition of drift velocity? Definition, it is the average velocity, which is the average velocity with which free electrons in a conductor gets drifted. कैसे होगा? इस डायरेक्शन में होगा, electrons gets drifted opposite to the direction of the wave. So we must have to mention free electrons in a conductor gets drifted in a direction opposite to that of the applied electric field is known as drift velocity, and it is denoted by v suffix d. So this is all about drift velocity, and ultimately we find that the expression for drift velocity dt is equals to what? Minus small e capital E divided by m into tau, where this quantity, these terms represent symbols denote E, charge of an electron, this is electric field applied, this is mass of electron, and this is tau. What is meant by tau? Tau is the relaxation time between two successive collisions of free electrons. Now we will talk about another important term relating to drift velocity. This is mobility. So mobility, which is denoted by the symbol mu. Actually, for different materials, for conductors of different materials, we see that the velocity of electrons with which moves, that is, actually we are talking about drift velocity. So drift velocity for a particular conductor depends on the source of electric potential. What is the source applied across this conductor depends on this value. Suppose if we are applying here 10 volt source, then the velocity of electrons here will be certain value, and if it is reduced to 5 volt, then we will have something another value. That means this drift velocity actually depends on the potential difference applied across the conductor. So based on this, we have defined that mobility is the rate at which electrons get drifted. So we can define it like it is the drift velocity. It is the drift velocity when unit electric field is applied across the ends of a conductor. So mathematically it can be written as mu equals to drift velocity divided by electric field. Again, mu equals to drift velocity dd, and here it is electric field E. Now, if we replace the value of bd here, we will be getting E capital E by me into tau. Actually, in the expression of drift velocity bd, which is equals to minus E capital E by m into tau, there is a negative sign, but not necessarily we will be putting here a negative sign. You may use it or you may even skip it, because this mu is a scalar, but it's just a number. So always it's not necessary to use this negative sign. You may skip it better. So from this equation, here we see that E cancel out. So we are left with mu equals to E tau by m. This is the expression, mathematical form of mobility. And now if we find the unit, SI unit, mu equals to, we will consider in this equation. So Vd by E, and Vd is nothing but velocity, drift velocity. So it will have unit of meter per second. Electric field E. Electric field is the potential difference per unit charge. ये तो लोगों को इलेक्ट्रोस्टैटिक्स पार्ट में होता है सीधे जाएगा. So here we will be using it is Newton per coulomb. Newton per coulomb. So the expression becomes meter per second per Newton coulomb. This is the unit of mobility. Another old unit is also there, which is equals to meter square per second per voltage. This is another unit. Better you try to convert this unit into this form.